Hello, and welcome to part 4 of this series of videos that introduce the mathematics of signals. For a full playlist with all the parts of these series, please click the link at the top of the screen. In this part, we'll introduce real Fourier series. So first of all, an outline. We're going to formalise mathematically the idea from part 3 that other signals can be built up from time harmonic signals. We're going to answer questions such as, how is the amplitude of a time harmonic signal present within another signal computed? What features of time harmonic signals make this work? And then we're going to look at some examples.
Fourier series are named after a French mathematician called Joseph Fourier, who proposed them in 1807. The main core assumption behind Fourier series is that any periodic function can be approximated by a sum of sinusoidal functions with the same period. This was quite a controversial claim at the time. Now, I've written this specifically with functions here because Fourier series can be used for all sorts of purposes. In fact, Joseph Fourier proposed the idea while studying heat conduction. But we'll always be talking in terms of signals, i.e. functions of time. So we would probably say any periodic signal can be approximated by a sum of time-harmonic signals with the same period. So time-harmonic series is what I was calling sinusoidal signals in part 3 of this series. What might a periodic signal look like in a sort of general sense? We've talked about time-harmonic signals already. So this is here's a signal x versus time, and the signal could come along and it would do something, but after some time t, we'll call that big T, period, what we see is it basically repeats. So it just does the same thing again, whatever that is, and a second time, and then if you let it run, it'll just keep on doing the same thing again and again. So a periodic signal is just a signal that just keeps doing the same thing again and again and again, and it just has this one characteristic, which is its repeat time, big T. So that's what we're going to be thinking of in this part. The idea was actually later extended to non-periodic functions as the Fourier transform, and we're going to talk about that in part 8 of this series of talks. Fourier analysis is really important. It's now one of the most widely used tools for analysing signals. So it has two parts. It has a forward and a reverse transform. All flavours of Fourier transform have these two parts. You have a forward transform that performs analysis. You give it a time domain signal and it returns amplitudes and phases of all the frequency components that are present in the signal. And then we have a reverse transform that performs synthesis. So you give it amplitudes and phases for all the frequency components and it returns a time domain signal synthesized from them. And I particularly use the word synthesis here quite deliberately because it's essentially what a lot of synthesizers do in terms of the sort of electronic musical instruments. For the Fourier transform, you see that these two operations are very similar when we talk about them in part 8, but for Fourier series they differ. What we usually do is start by looking at the reverse transform and defining that, and then we will talk about how you might find the equivalent forward transform and the equivalent kind of amplitudes and phases from a signal. It's usually easier to synthesize a signal from frequency component than it is the other way around. So let's have a look at the reverse transform. As we said, we're assuming that the signal xt is periodic with period big T. That'll be in seconds. It follows that if that's true, then all the frequency components that comprise it must also be periodic with period t, because they need to repeat in the same pattern that the signal does. So the question becomes, what sinusoidal functions are periodic with period big T? Well, essentially we're going to be looking at the same sort of trigonometric functions that we were looking at in the last part. So an obvious one will be a cosine wave that does one cycle in period t, and we can write this like this, that we look at time little t and we divide it by the period big T, so that little ratio is going to go to 1 as you get to the end of this time period, and then if you multiply that by 2 pi, that gives you radians, so we do 2 pi radians a full cycle, every time little t gets up to some multiple of big T, and that will give us the cosine shape there. But what else could we do? Well, we could actually do more than one cycle. We could do 2 cycles. So here we could double the number of cycles. We could double the frequency by changing that to 4 pi instead of 2 pi. Now we do 2 cycles in that period. That's still periodic with time t. I mean, it's actually periodic with time t over 2 as well, but it's still periodic with time t, just does 2 cycles rather than 1. And we can continue to build this up, so we could do 3 cycles in time big T, and that would also be valid. Or we could do 4 cycles, etc., etc. Just keep on building these components up. So any of these would satisfy this criteria of being periodic with period T. But we don't have to be stuck with cosines, we can use sines as well. So what could we have there? Well, again, we could have just 1 cycle like that. And that's just got the same frequency, angular frequency in it as the cosine term. Or we could do 2 cycles, or we could do 3 cycles, or we could do 4 cycles. They all have their own sort of shorter period, but they still satisfy this longer time repeat period as well. So that is the sort of families of functions we'll use. And generally what we'll write is we'll write that they're cos 2 pi fnt or sine 2 pi fnt, where f is some what we call a kind of harmonic frequency. So you'll have heard this term in terms of waves on a string, particularly the sine functions on the right hand side look a lot like possible wave shapes that might exist on a string. And these frequencies are integer multiples of 1 over t. So the lowest harmonic is repeating in t seconds, so it's got a frequency of 1 over big T. And then you've got harmonics of that, which are at multiples, integer multiples of the frequencies, and they are at n over big T. So those are the harmonics of this particular time period, big T. So that's our family of functions. We're just going to want to use any mixture of all of those with possibly different coefficients. We could possibly have some constant offset as well. This is also sort of periodic by definition. If it never changes, then, you know, the next period will be the same as the first period because nothing's different. You can also think of this as a cosine wave with 0 frequency because cos 0 is 1 as well. The question is how to write this mathematically. We're going to do it like this. So our signal on the left hand side is some constant term a0 over 2. Now the over 2 is just to make the forward transform look a bit more kind of uniform later on. And then we have the summation over order from n equals 1 up to infinity, however high you want to go. We'll have the cos term and the sine term, both of these harmonic frequencies fn, which are related to big T, the time period. And then they each have their own little coefficient an and bn that scales them. And these are all real numbers. And it's worth noting that an and bn, and a0 for that matter, all have the same units as x. Now just before we take this a bit further, just a little aside. In the previous talk I was writing things like amplitude a times cos omega t times phi. Now we could write a version of Fourier series that way too. Now I've chosen not to use omega here because I'm just trying to emphasise these harmonic frequencies, but we could write something like this, and I've used C for amplitude here just so it's a different letter. So we could write something like C0 over 2, still a constant factor, but then rather than having this cos and sine, we could just have coses and then have a little phi n in there as well, give each harmonic possible little phase offset phi n, and then an amplitude as well. And this actually achieves exactly the same thing as the Fourier series above. And that is because of this trigonometric identity. If you have the summation of two terms instead of cosine, then you can split it out and you get some products of different terms. And we found that the original sort of cos 2 pi fnt turns out with a cos phi n, and then the sine 2 pi fnt comes out with a minus sine phi n. So basically we can see that an in the Fourier series, as we've written at the top, is equivalent to cn with cos phi n, and bn is equivalent to minus cn with sine phi n. So they're doing the same thing. In this series at the top, we've got 2 degrees of freedom for each frequency, an and bn. In this other one, I've just written in the green box, then you've got Cn and phi-n, but you'll find that an and bn are much easier to solve for, particularly the phi-n would be, because they're linear factors. They're not stuck inside a sinusoid as the kind of extra phase term. They're just out the front as a multiplying scalar, and that is an awful lot easier to deal with. So just a little aside there, we were talking particularly about phase of different signals, but for these real Fourier series, we'll find it's easier to find these an and bn coefficients. Right, so how might this work, this particular series? And we're gonna start off by looking at an example we saw last time, which was the sawtooth signal. So here it is. It's got this kind of characteristic sawtooth pattern like that. And this is the equation for it, which I explained in the last lecture, where t is the period of this wave. And you can build this up as a sum of sine functions. So we're not using causes here, we're just using sines. But we've got an fn then, and this is following the same pattern that we're now using for the Fourier series. These harmonic frequencies are the same. And I was just showing last time, I'll show it again now, how this converged. So if you truncate the series, the maximum number at big N, and then you look at how these add in, we'll look at that as the red line, and then we'll see all the individual terms of the sines as the little grey lines. So if I just run this, we'll start to see some other terms coming in there. And as you increase the number of terms, big N's on the bottom right hand side of the graph, then you see it gets gradually closer and closer. There's still a bit of a wibble, and of course we get this sort of like increasing wibble towards the discontinuities, the jumps in the signal, because it has to try and sort of approximate this jump with smooth functions, and that's called Gibbs artifacts. So let's compare this example we've already seen to Fourier series. So let's get up our equation here for the reverse transform, the synthesis with Fourier series. And if we just compare the two, it's relatively straightforward. So you can just look at the different terms. You can see the sine terms turn up the same, and it's obvious that all the an terms, including the a naught, are all going to be 0 for any n, but the bn terms are going to be minus 2 over n pi. That's what they come out as. So effectively we've actually done a Fourier series already last time, we just didn't call it that. So let's now go on to think about how you actually find out these ANs and BN, what numbers they are. You can see that this particular signal was given by this particular combination of values. How might you work those out? So that is the forward transform. We need to find AN and BN from xt. And the way that we'll do that is using an integral. These are what they look like. So we've got a little normalization, quantity 2 over t, and then we do an integral from 0 to t over one period of the signal times the component that we're looking for. So if we're looking for cos 2 pi fn t, then we multiply it by that, and then we integrate that over a time period. If we're trying to find out how much of sine 2 pi fn t is in the signal, it's given by bn, multiply the signal by it, integrate it over a time period, put in this normalization factor, and that comes straight out. Note that a naught is actually very similar as well, but cos of 0 is of course just 1, so there's nothing even to write there. It's just the average value of x over the time period. It's just the mean effectively with a normalization. And this is where that over 2 beforehand came in, because that just makes this a naught equation match the other one for other values of an. And it's just worth pointing out here that, like with the signal statistics in the last video for time harmonic waves, we only need to integrate over one period of xt. Because xt is periodic with time period big T, all the information's present then from t in the range 0 to big T. And the rest of the signal just repeats the same behaviour, so we don't need to look at it, we can just look at one period. And that is the answer kind of just there, really. That is what you have to work out. And if you're doing it in a computer, you could do it numerically. If you're doing it on paper, you could do it by hand. But the more interesting question is why does this work? And the answer actually comes from the reverse transform in a weird sort of way, from this combination of frequencies that we've chosen to use. So let's just have a look at these. So I've got my two integrals there that I had to work out to find an and bn minus the little scaling terms. and then I've got my reverse transform, how I get xt from a and b in just in the box. And if I substitute that in, what I'm going to get is a lot of terms. So I'm going to drop this in for xt, first of all in the one at the top, and I'm going to get a lot of terms. Essentially what I've done here is I've put the definition of xt in, and then I've split up all the terms. So I've split out all the integrals, including splitting up the summation, so the integrals come inside the summation and they happen separately for this cos term and the sine term. And then I've taken the coefficients, the ANs and the BNs, outside the integrals because they're just constant scaling factors, so they can go outside. And this is the first reason, as I say, why this is a lot easier to do than if we'd worked with an amplitude and phase system, because it's much harder to get phase outside an integral. Already we see that this thing's giving us the coefficients we want times by some sort of quantities. Now we're going to look at the sine term. We're going to do the same thing. We're just going to substitute the definition of xt into it, and there it is, and we get a whole load more terms and more integral terms. But now where we had the coses arriving from the cos that was written explicitly into the integral, we now have sine terms. So we're going to get some slightly different pairings turn up in all of these terms. Just one thing just to notice is that because I'm just trying to test whether this integral does what we expect it to, I've written fm, so I'm kind of assuming that we've got 2 pi fmt inside cos and sine there, and I'm thinking that this is going to be a harmonic frequency, but it might not necessarily be the right one, or at least we're saying what happens when we test with a harmonic frequency fm, which harmonic frequency pops out from the summation. So I've deliberately used n in the summation and m in the sort of testing integral in the actual transform. So we're going to see how those two come out and relate to one another. So there's a lot of integrals here, quite a lot to deal with. So I'm just going to give them all names. So the one that was just a cos, I'll call IC for just cos. The one that has two coses, I'll call ICC for cos. The one that was cos sine, I'll call ICS. The one for just for I sine, I'll call IS, and so on and so forth. So I'm just going to use that term just to refer to them onto the next slide. So here we're going to just go through, we're going to try and work through all of those and see what they do. So the first one is IC. It's probably the simplest one to deal with. It is just the integral of a cosine over a period. And basically what we're going to do here is try and exploit the same thing that we saw when talking about the mean value of a signal, or time-harmonic signal, which is just basically say that it's going to be negative as often as it's positive, and all of these are going to cancel out. So all these signals we're going to look at, because they're formed from these harmonic frequencies, will all have a certain number of complete periods within time 0 to t. So they're all essentially going to fulfill this property. The only time that doesn't happen is if the frequency in the bracket is 0. So if m or whatever's going in the cosine bracket equates to 0, then we will actually get a term out, because cos of 0 is 1, and then you integrate from 0 to t just times 1 and you get t. So the end result of this might look quite complicated, but it's actually quite simple. If it's oscillating, so if m's not equal to 0, then you're going to get 0 out of the integral, and if it's static, if it's just DC, if it's just stuck at 1, then you're going to get t. So let's do that. So then let's look at the sine term, and that's very similar, except that actually, so if it oscillates, you get nothing out, but actually if it doesn't oscillate, you also get nothing out, because sine of 0 is 0. So regardless of what you put in that, it's just always 0. So that's got the first two out. They're pretty simple. Now let's get into some of the ones with combinations. So cos and cos. So we've got two coses here, and one's got 2 pi m and one's got 2 pi n. What's this do? Well, we've got product of two functions here. It's a bit difficult to deal with. So what we'll do is we'll use a trigonometric identity to break that up into, rather than the product of two cosines, to be the sum of two cosines. And these are going to come out with slightly different frequencies. So one's going to have m minus n, and one's going to have m plus n. Now remembering that m and n are both integers and they're both greater than 0, you can see that the second integral is always going to be oscillating. M plus n is always going to be oscillating. It's always going to be doing something. At least one of these is always going to be greater than 0. So that's going to not come out with anything. But the one on the left hand side could give you something, because there we have the possibility that m equals n, and then the thing doesn't oscillate, it just sits there at 1. So you evaluate the integral from 0 to t of just 1 and you get big T. And then we've got half floating out the front there, so we're going to get t over 2. So we're going to get t over 2 when m equals n. So when the two things, the oscillation in the wave and the oscillation in the thing that was in that sort of transform integral are the same, and you're going to get 0 otherwise. Now let's look at the sine and the sine term. So this arose in the second integral, and again we've got the same format. One of these has got m in it and one of them's got n. And there's another very similar trigonometric identity that lets you expand that out into the sum of two things, and actually these are cosines again, perhaps quite surprisingly, that they're just subtracted rather than added. And we've actually already dealt with these. We know that the second one is 0. We know that the first one is t over 2 when m equals n and 0 otherwise, so the whole lot exactly the same as ICC is just t over 2 when m equals n and 0 otherwise. And finally we've got this cross term here, and this is going to give us something slightly different. We're going to have to use another trig rule again, and that's going to give us something with sines in, so it's a similar kind of form to the ones above, but we've got sines in there now. And again, anything in the second integral is always going to be oscillating, so that's always going to integrate to 0. But the first one, we have this possibility here that when m minus n goes to 0, because m equals n, that it could be non-oscillatory. But again, like IS, here we see that because it's a sine and sine of 0 is 0, we're just integrating 0. So again, regardless of what we do, we get 0. And I've just noted at the end there that ICS, the one where they're just flipped the other way around, is exactly the same. So you get 0 out of that one too. So this is the kind of key thing here, is that there's a whole stack of integrals here, but almost all of them are 0, and if they're not 0 then they have very, very clear predictable values, and this is because these sets of frequencies that we've chosen have a property called orthogonality, that if you look at these integrals of pairs of them of this way, you basically find that they'll always kind of cross-modulate and give you something that integrates to 0 unless you happen to have chosen exactly the same frequency. And then you've basically got frequency squared, and as we know, when you square a frequency and then integrate it, like doing the RMS, you will get something non-zero out. So that's essentially what we're seeing here. So the result of orthogonality. And this is a really, really important property for Fourier series. It's basically why they work, or it's why they work so easily. There are other ways of kind of interpolating a signal versus time, and a lot of them involve solving some sort of set of simultaneous equations or something to find all the coefficients, but Fourier doesn't do that. You just can find the coefficients directly without having to evaluate any other ones. If you want to know what is the amplitude at 100 Hz, you just bang in 100 Hz as your testing frequency and it will tell you the amplitude and phase. You don't need to even work the other ones out if you don't want to. And similarly, if you add, change levels of other frequencies, that doesn't change the amount of 100 Hz that's present. It's just something that's sort of a building block in its own right, and that is because these are orthogonal, that is true, that you can just regard them as all working independently from one another. So it's a really, really important property. That's basically why all of this frequency analysis works as well as it does. So let's go back to our previous slide and just try and plug in some of those results. So IC, that was 0 unless m equals 0, in which case it was t. And ICC, that was t over 2 if m equals n and 0 otherwise. ICS was always 0. Coming down to the bottom row, we have the first term IS was always 0. The second cross term was always 0. And finally, we have one that has some point when it is t over 2 when m equals n. So, looking at that, you can look at that top term and you can see that it would find AM, if you like. So AN for which n is equal to m. So it's going to pull that out, and if you just rearrange that equation and swap m for n, you'll just find the exact forward transform equation. It just basically does, you can just show that if you plug everything in, it just pulls out the coefficient that you want it to. Similarly with the sine, you put that in, you plug all this through, and it's going to pull out t over 2 times bm. So just rearrange that and change the name of m to n, and you get exactly the transform equation. So these things do what they say on the tin, and they do that because all these different frequency components are orthogonal. So now let's look at a second example. This is a square wave, and there we go. So another quite well-known wave, and you can write this again using a mod function. So this little mod function here just kind of keeps going up like a little sawtooth that's raised, so it keeps going from 0 to 1 in every time period. And if you just say that when it's smaller than a half, xt is going to be +1, and when it's bigger than a half, then xt is going to be -1, then you can create the nice periodic square wave structure like this. And again, kind of coming to the answer just by already knowing it, just for illustrations purposes, we'll see that this is also written in terms of a load of sine functions, but there's a few differences here. We've now got 4 out the front instead of -2 for the saw wave, and we only have them for odd n. So the saw wave had all the harmonics in it, but this only has ones where n is odd. So again, we can just see how this converges. I'll just define this term x with a little tilde on top in red, and we'll just see how, as you sort of truncate the series at some value big N at the bottom there, which is also written on the top right of the graph, as we change that, we'll just see how it approximates it. So first of all, we'll just see a sinusoid, and then we'll start to see some other terms add in as well, and this thing will kind of like gradually get closer and closer to a square wave, albeit with a bit of a ripple on top and some Gibbs artifacts near the edges. Let's just see that one more time. There's this first term, 2 terms, 3 times 5, 7. We're going up just on the odd numbers here, of course. There's no point showing the even ones because nothing changes. So in the same way as square wave, we sort of get nice and close in the smooth bits, and then where you've got discontinuity, it causes these Gibbs artifacts, this kind of rippling. So let's compare that to our Fourier series. That's the form of that. By just comparing the two, you can again see that an is 0 for all n, but rather than bn being 2 over n pi for all n, it's now 4 over n pi and only for odd n, otherwise it's 0. I could just compare those on a graph like this if you wanted. You'll see they're both kind of the amplitudes of different frequency components is dropping off as the harmonic order goes up. Square wave 1 is always double the sawtooth wave 1, but it only exists at every other harmonic number. So it's only got those odd harmonics present in it. So let's just try and understand how let's try and show why they take the values that they do. So we're just going to kind of go through this visually at first and just try and understand why they take those values. What I'm going to do first of all is I'm going to look at the A terms. I'm just going to show why they're 0. So we'll just take an and we'll take xt. And the tested integral was multiplying xt by cos 2 pi nt. So here's one period of our square wave there. And let's look at n equals 0 first of all. So this is the DC component. So we're doing square wave times constant gives you, of course, just the square wave. You integrate that, as much of it's positive as negative, it integrates to 0. The mean of the square wave is 0. We kind of could see that from the graph, to be honest. So let's move on to n equals 1. Now we've still got the same square wave. We've got one period of a cosine wave. If we look at the term in the graph, the products of the two at the end, we'll see that it kind of gets flipped halfway through the cycle. And again, we're going to look at, because we're integrating, we're looking at the area under the curve. As much as positive as is negative, so it just goes to 0. Again, nothing there. To convince ourselves a bit more, let's just go up to n equals 2. So now we've got a cosine that does two periods within 0 to big T. What does that do on the right? Well, again, it sort of gets the second half of it sine flipped. But if we look at the area under the curve, we still see that it all just cancels itself out, and we just get 0. So, and this pattern would just continue if we looked at the cosine term. So they're all the an's going to be 0. which is what we saw already. So let's go over and look at the bn's instead, the sine terms. So now we've got a sine in the second graph. No point in looking at n equals 0 because sine of 0 is 0, so we'll start with n equals 1. So we've got one period there of the sine graph, and let's just see what the square wave does to that. Well, it actually flips the second half positive, so rather than going negative it just stays positive. So now I've got positive, and that is not equal to 0. It is equal to something that we'll have to evaluate. Great. Okay, so we'll have a look at that. I'll come back to that in a minute. What about 2? So this was the one that we found was 0 in the series. It's even, so it should be 0. So there is our sine wave for 2 periods. Then we multiply it by the square wave, and the second one gets its polarity flipped. So let's have a look at the curve under the area of the curve under there, and yeah, they're just all going to cancel out because there's as much negative as there is positive. So essentially this is because the sine wave has done a full period within each half of the square wave, within each t over 2. So you can see that although the second half of the wave got flipped, each of those individual ones was just cancelling itself out anyway, so we're not getting anything. Now we move on to n equals 3, and now we get a situation where we do 3 cycles in 0 to time t. So the square wave is going to flip those when we multiply it again, the second half of it. But the difference here is that before we get to the flip point, we've only done a cycle and a half. And that means that there was actually more positive than negative in that first cycle. And then that holds also for the second flipped cycle. And of course that's going to not equal to 0. So this is essentially the reason why the odd harmonics give us something non-zero here, whereas the even ones don't. It's because they're doing incomplete cycles in each half period of the square wave. So when you get this kind of flip, you actually flip up something that's got some non-zero component. So if I go back to n equals 1, you can see that we had sort of positive behaviour pretty much all the way through. So this is going to be probably quite significant. Whereas if we go to n equals 3, we've got some cancellation plus and minus, then a bit of extra positive, and some more cancellation plus and minus, and then some more positive. So compared to that n equals 1, we're only seeing a third of this period actually contributing some net positive behaviour to the integral. So this is where we get the 1 over n in the term as well. So that's doing it all graphically, and I hope that's been helpful. However, if we actually want to work out the values, we're going to have to rattle through this numerically. So let's just do that. So there's our integral there that we're going to evaluate. First thing we're going to do is just put in the definition of xt. It's positive for 0 to t over 2, then it's negative from t over 2 to big T. So we've just sort of put in 1 and minus 1 into those, and that's why the second one's subtracted. However, we know that because of the behaviour of the sine wave, it's always going to have a flipped behaviour in the second half. So actually that second part of that integral is actually going to be equal to the first one, and we can just double it and just look at the first one. So let's have a quick look at that. If we do that integral, then sine goes to minus cos, and we have to divide by the multiplying term inside the bracket. So we've divided by 2 pi n over t. And that's exactly where that's come from. And then we need to evaluate this for little t equals 0 and little t equals t over big T over 2. So doing that, we will get this expression here, where for the first term we've put in big T over 2 for little t, and that's cancelled with the 2 and the big T that were there already, so we just get cos of pi n. And then the second term coming from the t equals 0, cos of 0 is just 1, so that's where the second term here has turned up. And if we just gather a few terms and simplify things outside the bracket, we can see that we get a 2 over pi n times 1 minus cos of pi n. And cos of pi n is 1 when a wave is of even n, and it is minus 1 when the order of the wave is odd, when n is odd. So putting those two things together, we will see that when they're even, it's going to cancel out and that bracket's going to be 0. When they're odd, the bracket's going to be 2. So cumulatively we'll get the 4 over pi n for n equals odd, which is what we were expecting. So that was proving that we got what we got. Final little point here, which is something that we've just exploited kind of in doing some of these things, and we've started to see it. It's just the idea of symmetry and even symmetry and odd symmetry. A wave with even symmetry, or a signal with even symmetry, would be one where x of minus t is equal to x of plus t. So you can see on this wave here, it's a complete mirror image that time at minus t is the same as time plus t. And cos follows this rule. Cos of minus theta is cos of theta. And as you kind of seen in some of this working through with the square wave, that if the sort of symmetry of the wave you're evaluating follows the symmetry of the time harmonic wave you're putting in, then you get non-zero behaviour come out. So in this case, we will find that for any wave with even symmetry, it's only got cosine terms, so all your bn equals 0. And this is really useful because, as we saw before, what we're often doing is getting a lot of integrals, and a lot of them actually work out as being 0. And you can just save an awful lot of time and effort if you can just immediately spot the ones that are going to be 0 and just say they're 0 and not have to even work them through. So anything that's got even symmetry, you know that all the bn's are going to be 0, all the sine terms are going to be 0, so you only got to work through the cosine terms. The other possibility is you might get odd symmetry, which is when a time reverse version of a wave x minus t is the negative version of it going in the forward direction. That's what you see here on this particular little graph. It looks rather like the wave has sort of been spun round 180 degrees to make itself like a sort of rotational symmetry almost. And sine follows this rule because sine is minus theta is minus sine of theta. That's an identity for sine. And let's see with the square wave, then this was exactly what we saw, was that because sine followed the same symmetry patterns as the wave did, that when you started looking at products of them and integrating them, you were mostly getting stuff that was squared, and that was giving you something non-zero, whereas when you put the wave with something that had even symmetry, you're finding the two halves of the period cancelled out. So if you've got odd symmetry, you get all A0 equals 0. So you don't even have to bother working out the cosine strengths because you just know they're going to be 0. And just to give a last little example, it can depend on where you put the wave as well, because we've got a square wave like this, it's going to have odd symmetry. So you're going to have x of minus t is minus x of t. All an equal 0 and beta follow the pattern we've already seen. But if you took that same wave and you just shifted a little bit, then actually, just by changing the phase, you could get even symmetry. So now we would have that x minus t equals xt, and all bn equals 0, and now the an's take the form that the bn's did, because we just shifted a little bit. And of course, this sort of makes logical sense, because sine waves sort of shifted back 90 degrees, or pi over 2, are cosine waves, so that of course makes total sense mathematically. But I just think it's quite interesting to think that, you know, it's not just the fact that it's a square wave that makes it have this property, it's where you kind of define time equals 0 to be as well. So it's not just the wave type, it's kind of how you set it up a little bit as well. So that was the end. So a quick summary here. We have mathematically formalised the idea that other signals can be built up from time harmonic signals. We've looked at the forward transform, which I like to call analysis, and this is the process of finding the Fourier series coefficients from the signal. So basically what you're doing is you're finding the underlying mixture of sinusoidal time harmonic signals present in a signal. You're finding their amplitudes, which of course have the same units as the signal, and their phases. And in the standard Fourier series, these are brought out as two separate amplitudes of cos and sine terms. The reverse transform, which I like to call synthesis, is the creation of a signal from the Fourier series coefficients. So synthesis being the same word as synthesizers in electronic music. And we've also seen that if evaluating the forward transform by hand, it's well worth looking out for integrals that are zero and exploiting symmetry, be that kind of odd or even symmetry in the signal. There's going to be an awful lot of integrals. Most of them are going to be zero. If you can avoid having to work them out by hand, that's going to save you an awful lot of time. So that is very beneficial. And finally, we've seen again that if you truncate the Fourier series, then it causes kind of ringing and errors in the approximation. And when you sort of happen around steps, these are called Gibbs artifacts. We've seen those in the sawtooth wave and the square wave. And that is all for now. So next time in part 5, we will look at why time harmonic signals follow from functions from trigonometry. Thank you.